Hi folks, this is Mod 7. We're looking at problem 3, and this is part 2. We've already done part 1 and talked about the solution of the linear program, or at least the setting up of the linear program. What we're going to do in part 2 is we're going to take the information that we've gathered, and we're going to apply something called the simplex method, which is how these solutions are arrived at. So let's see what we've got with our worksheet. You recall in problem 3 that we had a budget problem. It was it's a budget allocation problem to an investment, and we had two types of variables, two variables: the number of shares invested in I and the number of shares invested in G. We had 4 elements of a strategy that we had to live by. And additionally, we had a budgetary constraint that said, all I've got is $10,000. I can't invest any more than that. We solved the problem, or at least set the problem up, and we determined that the objective function was 213 times I, 273.75 times G. Of course, you know that came from the fact that we had an initial cost of the investment of $200. In 1 year, if we have a 6.5% growth rate, that'll be 213. The original cost of a share of G was 250, and at a 9.5% growth rate, 250 turns into 273.75. So here's our objective function. We're going to try to maximize that. Obviously, we're interested in maximizing our return, but it's subject to these 5 constraints that we've set up: the budget constraints and then the 4 strategy constraints. So the question is, how do we set this up for permitting our program to begin to solve the problem? And the problem, as we've identified it here. So let me talk a little bit about how we're going to do this. In general, there are 2 areas that we create for our problem structure. One is related to the objective function, the other is related to the constraint area. And what we have in the objective function are a number of important pieces of information. First of all, we're going to have a row that represents what are known as the changing area. Changing area is where our program makes changes to the values of I and G and looks for the best combination. So we need to allow that. And you need to put a number in there. And I usually start by putting 1 and 1 in there. It doesn't really matter what you put in, but I generally use 1 in each one of these. Here we have some information about the price of the shares. Originally, here's the new coefficients associated with the return after 1 year. And the other important cell here is the objective function. The reason I put these values here, the objective function coefficients 213 and 273.75, is so where I can calculate my objective function value. And currently, if I have 1 share of I and 1 share of G, at the end of 1 year, I will return $486.75. Why? Well, because this value of the objective function is equal to this number of shares times this objective function coefficient plus this number of shares times this objective function coefficient. So that's the way we calculate our objective function. And by the way, the program will do this for you. All you have to do is provide an area for it. In this area, we create an area for our constraints. And what you will see in these light blue cells are coefficients. These are the coefficients associated with the constraint set: 200, 250, 200, 250, 1 in front of the I and 1 in front of the G. So these are constraints that are coefficients that are in front of the variables I, and G that form our constraints. Remember also that for every linear program in the constraint set, there's a left-hand side and there's a right-hand side. The right-hand side is what's on the right of the inequality, or it could be an equality, and the left-hand side is what is on the left of the inequality. And it's important to be able to calculate those two values, the left-hand side and the right-hand side. And you can see I've dedicated a column. These are just numbers that I placed here. I've dedicated a column to calculating the left-hand side. The left-hand side is equal to this particular coefficient times the decision variable plus this coefficient times the decision variable. And notice that I put dollar signs in front of the P and the 9. Why? Because I want to reference in an absolute fashion the decision variables, and I pull down that formula, and it does that. So since there's nothing here, the problem assumes it's a 0, so 200 times 1 is equal to 200. 0 times 1 is equal to 0, so this is 200. And you can see how I've arranged my coefficients here. So now I have my left-hand side, and I have a inequality here that represents the inequality for my constraint set, less than, less than, less than, greater than, and greater than. And then the right-hand side. The right-hand side in this darker blue are the values that are given in the problem. I have $10,000 budget. I can only spend 60% of my budget on I can only spend 75% of my budget on G. I must have at least 10 shares of I and at least 15 shares of G. So now let's go to the program and see how we're going to solve this problem. How Solver will place values in these cells to determine the best outcome here. Let's go to Data. Let's go to Solver. And what you get is this basic area here for information that we want to insert the solver parameters. Set the objective to be this cell. This is our golden cell. I want to maximize, so I put a maximization in this button. I could have done a minimization, but I'm going to maximize, obviously in this problem, by changing variable cells. These are the variable cells are located here. So I input that, and it says, okay, those are the cells that I'm going to change in order to get the best value of the objective function. Now I want to add my constraint set. So I hit Add here and said, all right, where's your first constraint? The left-hand side is less than, by the way, this is a pull-down menu, so if it's a greater than or equal, I can change that. We can also set these variables up to be integers too. Later we'll talk about that. So the left-hand side is less than or equal to the right-hand side. I add another constraint. The left-hand side is less than or equal to the right-hand side of the strategy 1. I add another constraint. The left-hand side is greater than or equal to the right-hand side for strategy 2. The left-hand side is now greater than or equal to the right-hand side. I add that, and then one more. The left-hand side is greater than or equal to the right-hand side. Hit OK. And here are my constraints. Left-hand side, this is column R. R15, 16, 17, 18, and 19 are less than or equal to for the first three for column T, and greater than or equal to for column T. Okay, now we select the simplex LP method. There are other methods, but these are for other kinds of nonlinear optimization. And so we select the simplex method and we hit solve. It tells us we have a solution And the solution, by the way, has been inserted into the problem here. The solution is the largest possible value is 10,875, and that is a result of having 12.5 shares of I and 30 shares of G. So I want to keep my solution. I want the answer report and the sensitivity report. I hit OK, and I get an answer report here and a sensitivity report here. Now, the sensitivity report we'll talk about in a little while, but the answer report simply says, all right, here's the value of the objective function that's maximized, and here are the values of I and G that represent the decision variable value I and decision variable value G. Down here we have some information that corresponds to the constraints. It tells us that the first constraint, which is our budget constraint, is binding. That means we used all our budget. The left-hand side is equal to the right-hand side, so we exhausted our budget. The second, the first strategy constraint is not binding. The second one is. So again, the left-hand side is equal to the right-hand side. Let's look at a solution again. I have cut and pasted these outcomes here. So the answer to B is, here's the objective function that's maximized at 10,875. So in other words, my $10,000 budget led to an $875 increase through the investment of 12.5 I and 30 shares of G. The next question asks, what if an additional dollar of budget could be had? Without resolving the problem, what's the new optimal solution? Well, the first thing we note is that since our budget constraint is binding, in other words, I've used up all my budget, the left-hand side is equal to the right-hand side, there is benefit to having one more dollar of budget. If it were not binding, then there would be no benefit because I didn't use it all up. So what is the value of an additional dollar of the budget? Well, that comes in something called the shadow price, or sometimes called the dual price in other programs. They're synonymous. Dual price, shadow price are the same. The shadow price for the budgetary constraint is 1.065. Now, only binding constraints have shadow prices. So the first one and the third one had a shadow price. The strategy 1, 3, and 4 are not binding, so the left-hand side is not equal to the right-hand side. And this tells us that if I had one more dollar of budget, I could return $1.06.50. So the new solution to the problem is going to be that rather than having a return of 10,875, I will have a return of $10,876.065. And that sensitivity analysis, that ability to make a statement about the value, the economic value of an additional resource, in this case another dollar. Let's say you found this in the sofa cushion someplace. You said, I had Aunt Lupe's $10,000 after she passed, and now I've got $10,001. And of course, with that $1, we're going to buy an additional share, or 1/200th of a share of I, because G shares are going to remain binding, and so I can't get any more G. I'd like to have more G because it has a higher return, but I've exhausted G because it's binding, and so I can get more shares of I. All right, that concludes the solver solution to problem 3 in Mod 7, and this is part 2 of problem 3.